Starting off with the diagram early here. And that's because I want to gain some momentum talking about ammonia and how complicated it gets when we look at what nature does. If bacteria produce ammonia, how did bacteria get here? Ammonia was here in very small amounts before the animals and plants. So if you notice here, N2 inert. That's because N2 doesn't really react with anything. It's got that triple bond. And then it says energy sources. Well, here's the energy sources, which are violent energy sources: lightning, ultraviolet radiation, volcanoes, and hydrothermal vents. In other words, that's, well, what I would say is the Earth is super hot. And when did that happen? Oh, billions of years ago. So we got small amounts of reactive hydrogen, meaning it's in this form: ammonia and a couple different nitrate ions. And those nitrate ions can combine with other atoms and form compounds. Primordial ammonia accumulates in pools and oceans. This is the primordial stuff was created by these things up here. Reaction with other molecules: water, methane, hydrogen, formation of simple biomolecules, amino acids, nucleotides, and sugars. And from these components, we can actually come up with the substance ATP, which creates the chemical energy that will allow bacteria to create ammonia. But you got to have bacteria around. Early metabolic networks in protocells. So here we're down here and things are alive. And then selection for controlled nitrogen supply. Let's scroll up here a little bit so we get the whole thing on the screen. Amino acids, nucleotides, early metabolic networks, evolution of enzymatic nitrogen fixation. Now see, I told you about that ATP. That shows up. ATP-dependent nitrogenase and the iron molybdenum formations. This is all super complicated organic chemistry. Sustainable ammonia production inside cells, and then support synthesis, amino acids, ATP, and then you have the modern biological nitrogen. We've already done a computer model of ammonia, but what we want to do is model some of these kinds of things. From what I just stated, there was no man-made ammonia. So that means that until man could figure out a way to make ammonia, there were no fertilizers. The Haber-Bosch industrial process. The energy source here is heat. It's not like lightning or anything like that, but you've got super high temperatures. Here's 400 to 500 degrees C, and super high pressure, 150 to 300 times the atmospheric pressure. And then you have some kind of metal involved here, and then you can go boom, boom, boom to ammonia. Then you can create ammonia gas and put it in canisters for the farmer, or you can create ammonium nitrate, which creates a compound with this ammonia in there. Thermal energy weakens bond. Okay. Yield scale, massive. Millions of tons a year. So that's where all the nitrogen comes that allows farmers to continue to produce crops on the same field over and over and over again. Here's the equation that represents the nitrogenase, which we're trying to do. If we could get all this stuff to happen, we wouldn't have to have all this energy intensive and CO2 producing process. This is the equation we're trying to come up with. N2, that's easy to come up with. Hydrogen, that's easy to come up with. Now here's the equation that we want to model the chemistry for. Nitrogen is available, hydrogen's available, ATP is this process here, but everything has to be in just the right state to make all this process happen. Now if we have a good model of these compounds, then we have a way of figuring out what the amounts should be and all the different other factors so that we can reproduce this synthetically. Here's the chemistry behind this ATP, and this ATP is important because this is what actually can produce the chemical energy. It's not going to heat things up very much. There'll be some heat lost, but this is the compound that's going to do all the work. These shapes, like this one, really represents carbons on each of these corners. And you can see carbon is actually shown up here. Now here's NH2. You think, oh, okay, well, there's the nitrogen. It's all by itself there. But this is not stable unless it's combined with carbon. So these nitrogens are not free to combine with the fertilizer action that the nitrogenase produces. And then we have some phosphates. Adenosine triphosphate. Boy, that was a mouthful, wasn't it? Now, modeling this stuff is complicated. Look at all those different atoms there. So to model this thing would take up a lot of computer power. In fact, more computer power than any classical computer can take care of it. So there, you can't use a simulation to find this. You have to actually come up with enough qubits so that it's fault tolerant, and then maybe we can come up to this solution. So that's the problem that I'm presenting here.